Our next speaker has sent a video introduction to help explain what he's going to be talking about today. Let's hit it.
The driving force of discovery in every field, from scientific to industrial, allowing researchers to understand the behavior of the smallest particles and visit the furthest expanses of the universe to unlock the meaning of life. And with digital twins, it's giving industries superpowers to time travel, letting them explore an infinite number of futures. And decipher the past through different lenses. And with million X higher performance, powered by accelerated computing, data center scalability, and AI, supercomputing will unlock new opportunities for us all.
And here to tell us more about a new era of digital twins, please welcome the Managing Director of NVIDIA Germany, Ludwig van Reiche. Welcome, the floor is yours.
Well, good afternoon, everybody. And first of all, I have to start with an apology. You booked your slot here to see someone else, but I'm afraid my colleague, Rev Leberedian, is not feeling so well today. So I'm stepping in here. You have to make do with me. In my day job, when I'm not on stage, I'm Managing Director of NVIDIA here in Germany, a company with about 500 almost here in Germany and otherwise, of course, around the world. I am now in the position to have 17 minutes and exactly 17 seconds here to take you through what is not a trivial subject, because we are combining three things that are not really that obviously stated in one sentence, namely supercomputing and the Internet of Things. And I would like to take you through a little bit of a context here first. Supercomputing, in many folks' eyes, is a supercomputer, a machine that costs millions, tens of millions of euros, and that is perhaps purchased by a research facility once every 5 or 10 years. Well, supercomputing, the way we look at this, is much more and goes beyond that. And that's where we would start actually with some very small components of that. You see here at the far left end of that slide, the edge, and at the far right end, the cloud. And our ambition here is to democratize supercomputing in two ways so that the research and the applications that you see at the top here can become much more widely used. But taking us back just a little bit, because many of you will know NVIDIA as the company of graphics. That was our founding premise 30 years ago. And it goes back even further. If you look at the animated hand from 1972, one of the seminal theses of Ed Catmull, who became one of the leading lights of the animation industry for the next 40 years. He made the hand move because he studied physics. And then later on came the very precise calculation of proper light. And those of you who are a little familiar with graphical computing know the Cornell box, because it has become a standard of assessing light in a physically correct and realistic way. And finally, this capability for physically correct lighting to make that happen and combine it with the physical world, that's what requires distributed ray tracing technology, which, by the way, to a considerable extent is developed by us here in Berlin at our lab. Now, looking at a virtual world, which in this case is a factory that I'm taking here as an example, but it could be another scenario just as well, and I'll get to some more, has to combine essentially these three things in as realistic a manner as possible. Rendering the physically correct and representation of light, because we want the images that are being represented to be as photorealistic as possible. I'll come back to that in a minute. A second capability that needs to be enabled in a world, in a simulation of a real environment, is physics. Of course, when you build a factory, it needs to be physically accurate. It needs to represent the physical capabilities of that. And finally, AI and the capabilities that AI brings to the table, they become particularly apparent when we combine the digital and the physical, and that's the modern interpretation of a digital twin. Now, if BMW designs a new factory, and I mention them because we're contributing a little bit to their new factories. If they do that, they use all sorts of computer-aided design tools, engineering tools, in order to spec out the factory and ultimately have it built. And if an architect designs a new skyscraper, they use computer-aided design software to build it and to design it. And then it is being built. And what happens traditionally to all the digital designs? Well, they sit on some machine, they get stored, and that's basically where they stay. Now, there is building information management, but that is not exactly what we're looking at, because we're looking at a true digital twin, namely an interaction between the real physical world and the virtual world as it is being designed originally, and then further enhanced based on feedback from the physical world. And that's what the sensors up there represent. The input from sensors and controllers in buildings, in machines that sense, for instance, the tear and wear of a production line. And ultimately, also the way humans interact with the physical world, to reflect that again in the digital world, so that it can be optimized as we go along. Now, this example here from an automotive factory is just one, but it is one that perhaps explains more easily than others what this means. But I have a couple more examples here. And they essentially start out with a somewhat fanciful concept, perhaps. You have seen science fiction movies, and you have teleported yourself into some kind of world if you're a gamer. And that's basically some element of that enters a digital twin, because it allows a factory line worker in China to teleport themselves into the digital model, which is designed and used to run not just the factory in China, but the ones in Germany and in Hungary as well. And it allows a researcher to actually look at what happened in their model, perhaps an hour ago, perhaps a year ago, provided the data that is fed back from the real world into the digital model is being retained. And so that's where an element of the digital twin technology can come to play in all sorts of applications. Another application, for instance, is currently being evolved by Ericsson. we're simulating cities to optimize the propagation of 5G telephony waves. At the same time, in the context of a city or a built environment, the data obtained from sensors from moving cars can be used to optimize automobile flows and to consider, for instance, the live adjustment of signals, of traffic lights. And perhaps in a longer term, if there was an accident somewhere, to go back in time to revisit in the digital model what the risks were of a certain traffic situation. Now, of course, that's just one thing. Traveling to the future could be potentially even more powerful when you actually have not just a future, but alternate futures that you can consider. Alternate futures, again, in the example of the factory, how you arrange different production flows. And many times production flows in an automotive manufacturing environment have to be adjusted over time because on the same production line there may be different cars being built. There may be components from different vendors provided by the robots that roam the factory. And again, you have to hark back to the digital model in order to optimize it and error correct it, for instance. So we see applications of these models in many different areas, and what they all have in common is that they require considerable compute power at different levels. I mentioned the sensors, tiny or not quite so tiny, built into cars and moving robots, for instance. But then, in order to have that as a truly global model, it requires real-time compute of a very high precision timing capacity. I'll come back to that in a second, but basically it requires the best possible synchronization of the small and the largest, and that's what we are investing in and what we're beginning to roll out together with our customers in order to allow real-time simulation, like for instance in this third image here, from how material behaves in a certain situation. And the most challenging element of that is, of course, not some material that may be tested for its strength, but the car that has to behave in a certain way and whose behavior, and perhaps today still malbehavior, has to be analyzed as in real time. Now, we have evolved a platform technology for that. We call it Omniverse, another verse, which is a technology that we make available for companies in different industries to build their applications on them. And they're just built around certain standards that enable this technology because in a very wide and open way, because they are widely accepted open standards. You see these little blue dots here. Those of you who are a little familiar with computer graphics will know that the universal scene description language is one that was made available generally to the world by Pixar, who are truly experts in the field. And so that allow the description of an object, a physical one, to the same specification, whether it is coming out of a CAD system, an entertainment system, a specialized system to track radio waves and the like. So there is an entire host of companies that are subscribing to this and whose tools are available to use the technology to build digital twin systems without, and pardon the pun, reinventing the world, each of them, because it gives them the ability to talk to all the other applications and participants in this ecosystem, which is really the key to making it a meaningful digital twin environment. So there's a platform underpinning all this. It's, in our case, a high-end supercomputer optimized for real-time interaction on a global scale. But you may ask, well, how can I afford to use this on a global scale because I am a smaller company or a startup? And that's where the cloud system comes in, because this is not available. You don't have to invest millions into this system, but you can essentially timeshare it because it is built such that it can be used as a cloud technology. Now, to wrap this up, we expect digital twin technology based on the Omniverse platform to be used and to be available at different levels. Essentially, from the very small, the molecular, where in the medical applications in genetic simulation and genetic engineering, it is already used today, to the factory floor that I described. And it is not just the BMWs of this world that can afford to deploy this, but at the city level or built environment level. It doesn't have to be a complete city. It can be just a limited environment like this park, for instance, around this convention center that could be suitable to optimize this using such technology based on a CAD application. And finally, planetary. Now that's a little bit fanciful perhaps of a term, but on the other hand, when we're talking about climate change, it is a truly planetary phenomenon and a requirement. There's a requirement for far-reaching global solutions, as we all know. And so we are building a system that's one that we build ourselves. The others are being built by other partners, but we're building a system that hopefully will make a contribution ultimately to simulate not just the occasional hurricane development as weather simulation already works today, but more wide-reaching climate issues. And I trust that in another year or two at this conference we can show something more of this, and also how others can participate from the results in that. So today, it's primarily an application at the level of factories, warehouses, architects that use the digital twin technology to optimize their operations. But we're really confident that it will go way beyond that with the cloud-based availability of Omniverse. And with that, 32 seconds before the clock runs out, thank you very much for your attention.